Lumps of pure iron lay scattered on the ground in the Arizona desert, all around the rim of a hole, 3/4 of a mile across. In October of 1891, the chief geologist of the United States walked out there with a magnetic instrument, a needle in a case, the kind that swings when there's a mass of iron buried under your feet. He walked it down into the crater and back up around the rim. The needle never moved. So he wrote the crater up as a steam explosion and said the iron had landed there by coincidence. His name was Karl Gilbert, and he was, by a long way, the best field geologist in America. He worked for the United States Geological Survey, which maps the country's rocks for the government. He didn't guess. He built two competing explanations for the hole, worked out a test that would separate them, and ran the test honestly. He got a clean negative answer, and he published it, and it was wrong, and it stayed the official position on that crater for the better part of 70 years. I went looking into how that argument ended, and I came out of it thinking the ending is the best part. You've probably seen a picture of this crater. It's on the interstate east of Flagstaff. It has a visitor center and a gift shop, and it's called Meteor Crater, which rather gives away how the argument came out. What gets left out is everything in between. For decades, the survey's official position was that no meteorite had made that hole. A man spent his fortune and the last 26 years of his life trying to prove otherwise, and he died having failed. And when the proof finally did arrive, it didn't come out of the crater at all. It came out of a nuclear weapons test site in the Nevada desert, and out of a chip of sandstone that went to Washington in an envelope. 70 years is a long time to argue about a hole in the ground, and the reason it took that long is the thing worth staying for. The evidence everybody was hunting had evaporated, in the literal sense, about 49,000 years ago. It took until 1960 for anyone to work out that you could read what it left behind instead. The crater sits on a flat plain of scrub and rock in northern Arizona, 37 miles east of Flagstaff, and it runs about 3,900 feet from rim to rim and 560 feet down. Its raised edge sits another 148 feet above the surrounding ground, so from the crater floor, the top is a little over 700 feet above your head. It isn't subtle. You can see it from an airplane and you can see it from the road, and lying around it, out across the desert, there was metal. Chunks of nickel and iron, close to pure, the kind you normally only get by smelting ore in a furnace. Some you could put in a pocket, and some you couldn't lift off the ground. People had been picking them up out there for years. So when Gilbert came out from Washington, he had a hole, and he had the metal, and the obvious idea had already occurred to him. But obvious ideas are exactly what a good geologist is supposed to test, so he set up two. If a huge iron mass had punched this crater, then two things had to be true. The mass had to still be in there, buried under the floor, because iron that size doesn't vanish, and the crater had to be bigger than the pile of debris thrown out of it, because the meteorite itself would be taking up room down there. So he measured. He surveyed the volume of the hole, and the volume of the material heaped around the rim, and they came out the same, about 82 million cubic yards each. No extra room for a buried mass. Then he ran the magnetic survey, and there was no deflection anywhere between the rim and the interior. Two tests, two negatives. His assistant, Willard Johnson, suggested the alternative, and Gilbert took it. This was a steam explosion, the kind you get when hot magma pushes up into groundwater, and the water flashes and blows a hole in the ground. There are old volcanoes in view from the rim, so it fit the neighborhood. He gave the conclusion in a lecture in Washington in 1895 and published it in the journal Science on the 3rd of January, 1896. 14 months after he walked that needle around the Arizona crater, Gilbert stood up in front of a room of scientists in Washington and argued that the craters on the moon, all of them, big and small, were made by things falling out of space and hitting it. He was right about the moon, and he'd already ruled that same explanation out for Arizona, and the two papers never mention each other. I've read a fair amount about Gilbert, and I still can't account for it, because his verdict was the survey's verdict, and the survey was the authority. The hole in Arizona was now officially a steam vent. That's where things stood when Daniel Barringer turned up. He was a mining engineer and a lawyer who'd made money in silver in Arizona. No geology department had ever heard of him. He was right, and Gilbert was wrong. In 1903, he staked a claim on the crater, filed under the Standard Iron Company, and got a land patent on 640 acres, signed by Theodore Roosevelt. He had no interest in settling a scientific argument. He was going mining. His arithmetic said the thing that dug the hole must have weighed something like 10 million tons, and iron sold by the ton, so somewhere under that crater floor was a fortune, and all he had to do was reach it. He drilled for 26 years. Shafts and boreholes all over the crater floor, one of them down to 1,376 feet, more than a quarter of a mile straight down. He found fragments, little pieces of the same metal that was lying on the surface, drill cuttings full of the stuff, enough to keep telling his investors they were close. He never found the mass. In 1929, the drill bit jammed for good, the cable broke, and the money ran out. He also found things nobody had asked him for. Rock at the rim tipped up past vertical and lying over backwards, as if the layers had been peeled off the ground and folded outward. And rock crushed so fine, it ran through your fingers like flour. He noticed all of it, he wrote it up, and none of it helped him, because it wasn't the thing he was looking for. There's something in Barringer I can't quite settle. He had the right answer years before anyone with a title did, and it ruined him anyway, because the prize he was digging for had stopped existing before any human being ever walked into Arizona. Then a mathematician named Forrest Ray Moulton, hired to settle the question for the investors, ran the numbers and handed back an answer that took the whole thing apart. The impactor was nowhere near 10 million tons. It was a few 100,000 at most, and it had been moving fast enough that hitting the ground would have turned most of it into vapor. There was no fortune down there, and there never had been. Moulton dated his final report the 23rd of November, 1929. Barringer read it, and on the 30th he had a heart attack and died. And the thing to understand about that failure is how it looked to everybody else. The test for an impact crater, the standard the whole field ran on, was simple and reasonable. Find the object. That's what makes a hole a meteorite crater. Barringer had spent 26 years and more than $500,000 applying that test to the most promising hole on Earth, and the test had returned nothing. So for the next 30 years the argument just sat there, unresolved, with the survey's steam verdict still on the books and no way to move it. Eugene Shoemaker was born in 1928, a year before Barringer died. By his mid-20s, he was a field geologist for the same survey, out on the Colorado Plateau mapping uranium deposits, which was ordinary work and nowhere near this argument. He had one private ambition that had nothing to do with uranium. He wanted to be the geologist who went to the moon, and he'd worked out that if anyone did go, they'd need somebody who understood what makes craters. Then, in the 1950s, the survey sent him to the Nevada test site, where the United States was setting off nuclear weapons underground and in shallow pits, to map what the explosions did to the ground, and he recognized the shape. At a crater called Teapot S, blown out on the 23rd of March, 1955, by a device buried 67 feet down, the rock at the rim was tipped up past vertical and folded over backwards, so the layers ran in the wrong order, oldest on top. It was the same thing Barringer had described in Arizona and been unable to use. Shoemaker went and looked at both. Here's how he described it years afterwards. I was astonished to discover that the structure of Meteor Crater was pretty much a scaled-up version of that of Teapot S. That's Shoemaker talking. Which is a good observation, and it's still only a resemblance. Two holes looking alike was never going to shift a verdict that had stood since 1891. What he needed was something inside the Arizona rock itself, something a bomb could put there, and a steam vent could not. Back to the needle that never moved. Gilbert's magnetic survey found no iron because there was no iron left to find. Barringer's drill found no mass for the same reason. Both men ran the right test on a crater where the answer had been vaporized, and that's what makes this problem interesting. The object that made the hole no longer existed. Every method anybody had was built to find it, so Shoemaker stopped looking for the object and started looking at what it had done to the rock. He collected samples of coconino sandstone from the crater, the pale layer that had taken the worst of the blow, and put them in an envelope addressed to a mineralogist at the survey in Washington named Edward Chao. There was a specific thing worth hoping for, and the odds against it were the point. 7 years earlier, in 1953, a chemist named Loring Coase, working for an abrasives company in Massachusetts, had taken ordinary quartz, the commonest mineral in the world, and squeezed it in a press until it collapsed into a denser version of itself, a new mineral. Making it took a few 100,000 pounds of pressure on every square inch, at a temperature around 1300 degrees Fahrenheit. You have to go tens of miles down inside the earth to find conditions like that occurring on their own. And a steam explosion in shallow groundwater doesn't come close. In the 7 years since Coase made the first grains of it, nobody had found the stuff anywhere in nature. Coase ran the powder through the X-ray and got a pattern back. He compared it against the pattern for the laboratory mineral. They matched. The paper ran in the journal Science on the 22nd of July, 1960. Volume 132. 3 authors, Chao and Shoemaker and Madsen, under a title with no drama in it at all. First natural occurrence of coesite. Coesite is what they called the new mineral, after Coase, who'd made the first grains of it in his press, and they reported it in the flattest language you will ever read. A substance that had only ever existed inside a laboratory was sitting in the crushed sandstone at Meteor Crater, in quantity. Barringer drilled 1,376 feet down hunting the thing that hit Arizona, and came up with nothing. The proof was in a chip of rock off the rim, and it weighed almost nothing at all. I find that extraordinary, and not for the reason you'd expect. The man who actually spotted it had never been to the crater. Ed Chao worked in a laboratory in Washington. He got sent a sample, and he read what was in it, and what was in it had been sitting in that sandstone, unchanged, for 49,000 years, waiting for somebody to invent a way to look. And the moment the way to look existed, it stopped being about Arizona. The next year, the same test was turned on the Ries crater in southern Germany, a wide, shallow basin people had been arguing about for a century, and there was the coesite. Then it went to the next one, and the next. A crater no longer had to have its meteorite still inside it to count. It only had to have been hit hard enough to leave a mark in the mineral. The Earth Impact Database, kept at the University of New Brunswick, currently lists 190 confirmed impact structures on this planet, and almost all of them were confirmed by the shock left in the rock. That's the work Shoemaker had built a field to do. He set up the survey's astrogeology unit, the group that applies ordinary geology to other worlds, in August of 1960, and moved its headquarters to Flagstaff in July of 1963, an hour up the road from the crater, because the crater was the classroom. He was the lunar geology investigator for Apollo 11, 12 and 13. And he took the astronauts out into that desert and taught them how to read ground like this, so that when they got up there they'd know what they were looking at. Some of this doesn't sit the way I'd like it to. Chao found the coesite. Shoemaker had sent the samples and worked out the geology. But it was Chao who ran the X-ray and recognized what he had. And the survey's own history of the branch says the two of them hadn't even met at that point. Shoemaker and Madsen went on the paper, so it carried a full survey team. That's how science usually works. The version that travels, though, is the one where a single man cracks it, and that version leaves Chao out of his own discovery. The second thing is that everyone called it a volcano for 70 years, is doing work it hasn't earned. Barringer and his partner were arguing impact in public from 1906. Herman Fairchild came out and agreed with them in print in 1930. What held for 70 years was the survey's official verdict, plus a standard of proof nobody could meet. And that combination is a slower, quieter kind of obstacle than a room full of people laughing at you. And I think Gilbert comes out of this well. He built a test, he ran it, he reported an answer he didn't want, and he published it. The reason he got it wrong is that in 1891, nobody on Earth knew what happens when something arrives at 26,000 miles an hour. At that speed, the impactor doesn't burrow in. It stops in an instant, and most of it turns to vapor. Roughly 300,000 tons came down. Everything anyone has ever found around that crater adds up to about 12,000 tons. Gilbert's needle told him exactly what was under the crater floor, which was nothing at all. He just thought that answered a different question. The numbers themselves still move. David Kring's review puts the energy of that impact at about 10 megatons of high explosive. Shoemaker's own working figure was 15, and later modeling he did with David Roddy ran it up to somewhere between 20 and 40. Then J. Milosh and Gareth Collins published a paper in Nature in 2005 that reworked the speed and brought the whole thing down to roughly 2.5 megatons. Take your pick. There's one more limit, and it's the one I'd undo if I could. In the summer of 1963, Shoemaker was diagnosed with Addison's disease, a failure of the adrenal glands. It cost him his flight status. He was turned down for a private pilot's license, and he was never going to be cleared to fly to the moon. He trained the men who went, and he watched them go from Arizona. Carolyn Porco, who worked with him, remembered him saying, only 2 years before he died, that not going to the moon and banging on it with his hammer had been the biggest disappointment in his life. So did one chip of rock settle a 70-year argument? It did, but only barely, and only because of what it made possible afterwards. The reversal here is that the evidence had been in the ground the whole time, in every impact crater on Earth, and for 70 years nobody knew it was evidence. That's the deeper lesson I take from it, I think. Gilbert went out there, looking for an object that had been gone for 49,000 years, and what the ground actually had for him was a record of what that object did on its way through. I think that second kind of evidence is the one that lasts. You can stand on the rim yourself. It's off Interstate 40, east of Flagstaff, and you can walk out along the north edge and look straight down 560 feet at the floor. The ruins of Barringer's mining camp are down there. So is the white scar of the main shaft, still open and still empty. And on the 31st of July, 1999, a NASA spacecraft called Lunar Prospector was steered deliberately into a permanently dark crater near the moon's south pole. It was carrying an ounce of Eugene Shoemaker's ashes in a small plastic capsule, wrapped in a square of brass foil, 1.5 inches across, laser etched with a picture of a comet, his favorite photograph of the Arizona crater, and a line from Romeo and Juliet. Take him and cut him out in little stars. So far, he is the only human being buried on another world. These are the stories I go looking for. A careful man runs a good test, gets an answer, and the answer holds for 70 years before anybody finds out it was the wrong one, for a reason nobody at the time could have seen. The history of science is full of them. Subscribe and I'll dig up the next one.